So if it were any arbitrary Cartesian system, the stress components, as we discussed, on each plane there would be three directions of stress components, or rather tractions. Okay, so eventually giving nine components of the stress tensor. So for example, let's take the front face. So on this one we'll have three components of traction. Okay, so which means I need a total of nine components to describe stress. And when associated with the angular momentum balance, we realize that there are only six independent components. The stress tensor itself is a symmetric matrix. uh, now with principal directions, uh, if we were to represent the differential geometry in the principal directions. Okay, so in that, if my differential element, okay, is in principal direction, like let's say this is the principal direction. Okay, so in that case, on each phase there is only the normal component of the traction. We showed that the shear components simply vanish. Okay, so in principal directions, so if I cut each so basically, uh, if there is a geometry, okay, under stress, and if I cut on a plane that is normal to one of the principal directions, let's say in one, then I'll only have the traction vector to be sigma 100. That's it. Now then again, this is the traction vector represented in the n1, n2, n3 coordinate system. Okay, so that needs to be cleared. Okay, um, traction vector would look something else if I were to represent that in uh, global Cartesian. Okay, uh, but the but the traction vector itself would be normal to the plane, which is the traction would be along the normal. Okay, the point I'm trying to make here is the normal itself, okay, doesn't look like 100 unless it is represented in the principal basis. Okay, and t would simply become sigma times n1, as we discussed, sigma 1 times n1, because this is where it comes from, the eigenvalue problem. Okay, so in the principal directions, this part we discussed already, that we can represent the stress components like this. So sigma 1, sigma 2, and sigma 3. And eventually the stress itself can be represented like a vector. Okay, and that's just only in the principal coordinates. Okay, if I were to represent that in a different coordinate system, the stress would look something else. But we'll stick to the tensorial representation of the stress, and that is in n1, n2, n3 coordinate system, and that would be simply this diagonal matrix. okay, and any arbitrary normal. Okay, now imagine I'm not saying that I'm taking n1, n2, and n3 as the directions. Okay, but I'm choosing n1, n2, and n3 as the basis of representing any vector on matrix. And if I do so, stress would be this diagonal matrix. Okay, I'm not saying that this point onwards, if I had to, take a section for a free body diagram on the body, I'm definitely going to do that with respect to either n1 or n2 or n3, a plane which is normal to either n1 or n2 or n3. I'll still be doing an arbitrary normal, okay, but that normal I'll simply represent with respect to n1, n2, and n3 coordinate system. Now again, this is only the beginning part where I'm just showing that the representation is only in n1, n2, and n3 coordinate system, and this would be some sort of direction cosines, right? Okay, where the relation is L squared plus m squared plus n squared equals 1. Or if I know two of the values, then let's say n squared is 1 minus L squared minus m squared. Is it clear up to this part?
Yes, sir.
Okay. Is it too much familiar? I mean, have you
Yes,
done
sir.
all of this? Huh?
Yes, sir. We have done this.
You have done this completely. Okay. Let's see. Uh, so the next thing that you do is, so the next part is we will try to evaluate the traction. Okay. So since you have done this, can you tell me what would be the expression for the traction in n1, n2, and n3 coordinate system? The traction simply is sigma times n. Okay. So if you really think about it, n is definitely L times n1 plus m times n2 plus n times n3. Okay, I choose poor representation of the direction cosines. Okay, let's call them nx, ny, nz, and this basically means nz squared is 1 minus nx squared minus ny squared. So this okay, again nx, ny, nz are not the correct representation. Let's call them alpha, beta, and gamma. Okay, so okay, so can you tell me what would be the expression for t? Now you see when I multiply with this n, see the multiplication with the matrix is a linear operation. Okay, so this would eventually be alpha times sigma n1 plus beta times sigma n2 and so on. Okay, now n1, n2, and n3, as we discussed, are the principal directions. So basically this one is going to be alpha times sigma 1 n1 plus beta times sigma 2 n2 and so on. So eventually it would look something like this. Okay, I mean, if you directly multiply this with this one, you are supposed to get the same answer. Okay, But for that, you need to have a representation with respect to n1, n2, n3 coordinate system, which we are doing indeed. But even if we didn't take the principal directions, we'll still be getting the same expression. That's the point. Now, now, as we discussed earlier, traction on a given plane. Okay, so let's say this is the normal to the plane, and this is the plane itself. So traction on a given plane can be decomposed into, not decomposed, can be resolved into two parts. So one is the normal component, the other one being the shear component. Now, can you tell me what is the expression for the square of the shear component?
1 minus t n square.
1 minus t n squared. No, the magnitude of t is not unity. Okay. Now, t squared is t dot t. And we don't need this representation for that. We can simply do it from here. Okay. So we'll just have to remember that n1 dot n1 is 1 and n1 dot n2 is 0. Okay. So that would eventually give us what expression? What is the value for t squared?
So sigma n1 square plus sigma n2 square plus sigma n3 square.
No. N1, N2, and N3 are all, you see, your vectors, unit vectors. Okay. So if you take a dot product, so basically what you are going to get is alpha squared sigma 1 squared. I mean, basically the magnitude of this thing, beta squared sigma 2 squared, and gamma squared sigma 3 squared. Okay. So in this expression, substitute this. Now, now Tn, of course, is the dot product of T with N. Okay. So that would be alpha times sigma 1 plus beta times sigma 2 plus gamma times sigma 3. Tn is not a vector. Tn is just the dot product. Okay. So then write down the expression for Tn squared. Remember, oh, sorry, I made a mistake. N is this quantity, right? So when you take a dot product, so it is alpha squared sigma 1, beta squared sigma 2, and gamma squared sigma 3. Okay. So now, can you write down the expression for TSS squared? Okay. And everywhere substitute this. So the final expression for TSS squared would be, are you getting the expression?
So it's coming alpha square into sigma 1 square minus sigma 1 minus sigma 3 square plus sigma 3 এরম টাইপের আসছে
Okay. Um,
প্লাস
so basically, the harder part would be to make a square of Tn. So Tn squared has a lot of terms, 6 terms to be precise. So, uh, so in that expression too, if you substitute for gamma squared, I believe you get something like this.
So 2 minus, sir, minus
Sorry.
2 alpha square, minus 2 alpha square beta square into bracket 1 minus alpha 1 minus alpha 3, sorry, sigma 1 minus sigma 3 into sigma 2 minus sigma 3. Minus 2 minus alpha square into sigma 1 minus sigma 3 into sigma 3. Uh, Minus 2 beta square sigma 2 minus sigma 3 into sigma 3.
Okay, so this is the total expression for TS squared. Okay, now I need you to give me the expression, because that should be zero. You see, alpha and beta are the two independent variables here, and should be equal to zero. So these two should give you two equations. So for example, the first one would be something like, okay, and the second expression, you can accordingly figure out what it should be. Okay, now now what we can do, what we can see rather, uh, both of these equations are satisfied by this, okay, then both the expressions should be 0. But then that would mean n is simply, so that would mean first of all gamma equals 1, and n would be, or n would be your n3. Okay, so one of the principal directions. But then we know that on the principal direction, the shear stresses or the shear traction, okay, is actually minimum. It is 0. And actually that is the result that you are getting, because setting the gradient to 0 can ensure there is an optimum, but that can either be a minima or a maxima. And as it turns out, taking both of these equal to 0, okay, you can get that minima. But we are definitely not looking for the minima, okay. So we're simply trying to get the maximum of TS square. Okay, so what do we do next is, so definitely alpha and beta are both not equal to 0. Okay, and as we can see that in from this expression, okay, we can divide either side with alpha, and that would lead us to the following equation. So we can divide either side with alpha, and also in general sigma 1 is not equal to sigma 3, so I can always divide either side with sigma 1 minus sigma 3. Okay, that is not true in general, but we are trying to get, I mean, of course there can be a situation when all the principal stresses are same, or at least two of them are same. It's a possibility, but that doesn't necessarily ensure, I mean, in general you can say that that is not true. Okay, and we are talking about a general situation here. So this eventually is your sigma 1 plus sigma 3. Okay, so if I divide either side with alpha, then I have this expression. And maybe I can also divide with 2. Okay, so is twice alpha squared sigma 1 minus sigma 3 plus twice beta squared sigma 2 minus sigma 3 minus sigma 1 plus sigma 3 and plus twice sigma 3. So basically this equals to sigma 1 minus sigma 3. And then in the similar way I can write the other equation. Okay, if I divide both sides with beta and sigma 2 minus sigma 3, so here I'm assuming alpha not equal 0 and beta not equal 0. So I have this expression, So ideally, we should be able to solve this two set of linear equations, linear in alpha squared and beta squared, to get the final expression, right? But can you tell me what is the problem here? Can you see the problem?
Sir, এটা প্যারাবোলিক ইকুয়েশন।
No, these are not parabolic equations. These are linear in alpha square and beta square. If you think of alpha square as x and beta square as y, so these are, you know, some coefficients, sigma 1, sigma 2, etc. And these are actually linear equations in alpha squared and beta squared. But the problem is the two equations are not independent. Actually, it's not that the system has infinite solution. The system has no solution because the two equations are inconsistent. You see, the left hand side is basically the same on either side. Okay. So when I put that in a matrix, the rank of the matrix, I mean, the rank of the matrix should be 0, right? Sorry, the rank of the matrix should be 1, and the determinant should be 0, and twice sigma 2 minus sigma 3 here, and twice sigma 2 minus sigma 3 here. So it's the same equation, right? I mean, but the thing is the right hand sides are different, okay, which makes it inconsistent. Okay. So in general, sigma 1 is also not equal to sigma 2, which basically means that this system is inconsistent. There is no solution that you can get out of it. Okay. Because the two equations, the same left hand side points to two different values in the right hand side in two equations. And if we assume this, then both must be true. And the two are inconsistent. So what do we get from it? So what should be our conclusion? You see, earlier we saw that taking alpha equals 0 and beta equals 0 does give us a solution, but that is not the solution that you're looking for. We are getting the minimum. Okay. So that's not what we can take. But if we take both not equal 0, then we end up having an inconsistent set of equations, okay, which doesn't give you any solution, which cannot happen, okay, because if this is assumed to be true, then these two equations should also be true, but these two equations cannot be true simultaneously, okay. The same left hand side cannot give two different right hand sides. So the only thing that is possible is neither both of them equal to 0 nor both of them not equal to 0. So one of them is 0 and other one of them is non-zero. Okay, that's the inference. So let's assume this time that alpha equals 0 and beta is not equal to 0. Okay. So if I assume alpha equals 0, the entire first equation gives you 0. So there is nothing to solve for. But in the second equation, if I assume alpha equals 0, so this goes to 0. Okay. And we are only left with terms of beta. Okay. Or for that matter, I mean, you can actually work with this equation. So over here, simply see this 2 is not from here, this 2 is actually from here. Okay, so on this second equation, so the first equation would never come, because you cannot divide either side of this equation with alpha, because alpha equals 0, so the entire thing is 0. Okay. But from the second equation, you can divide either side with beta and end up having this expression, but in that alpha equals 0, which would give us, what would be the value of beta squared then? Just assume this in general.
1/2.
Beta squared is 1 by 2. What is the value of beta?
Plus minus 1/2.
Minus 1.
Okay. So this is your very familiar expression, right? So what would be gamma also? Gamma should also be, plus minus 1 by root 2. And alpha is 0. Okay. So, so what does this mean? That directions of maximum shear I mean, this so basically your n looks like this, right? N is something like this: 0, 1 by root 2, plus minus 1 by root 2, plus minus 1 by root 2. You can take both of them plus. Okay. See, changing from plus to minus only changes the direction of the shear, but the shear component TSS squared is still be maximum. So so this is the in, but that I can switch places of alpha, beta, and gamma, and let's say end up having this solution also. Okay. So what does this mean? This means, first of all, I need to identify. So these are principal directions: n1, n2, and n3, and I'm looking for a normal, okay, to a plane in which the shear component of the traction is maximum, or TSS squared is the maximum. So for that, what we'll have to do, first of all, I'll have to choose one of the principal directions. Okay. And then I'll have to find out the plane that is normal to that direction. Let's say if I take n3, then that is the n1, n2 plane. And in that plane n1, n2, so I'm talking about this case right here. So this n right here is normal to n3. You see, if you multiply this with 0, 0, 1, if you take a dot product with n3, so that is 1 by root 2, 1 by root 2, 0, 0, 0, 1, taking a dot product, that would give you 0, right? So here, if I take my normal, making an angle of 45 degree with either of n1 and n2, then I'll have to imagine a plane that is normal to this, I mean, that is perpendicular to this normal. So on that plane, I'm going to have the maximum shear. Okay. So it is on that plane that I'm going to have the maximum shear. Now, the magnitude and the direction of the shear you can find out from this. Okay. So I'm just taking the example of this one. So times this, right? Or in other words, you can think of n to be 1 by root 2 n1 plus 1 by root 2 n2. Okay, it's not just this plane. I mean, instead of taking the normal in the first quadrant, I could be taking the normal over here also. Okay, again making 45-degree angles with either of the axis. And then imagine a plane. So this time it is normal with the earlier normal. Okay, so the plane also would be normal to the earlier plane. So on each of these planes that I'm going to experience the maximum shear. Okay, so if I do sigma times n, it is actually sigma 1 times 1 by root 2 times n1 plus sigma 2. So this is a traction. One by root 2 times n2 plus 0, okay, times n3. Now if I take dot product with n itself, so tn would be sigma 1 by 2 plus sigma 2 by 2. That is sigma 1 plus sigma 2 by 2. Whereas so tn squared would be square of this quantity, whereas t squared would be sigma 1 squared plus sigma 2 squared by 2. So if I now get the expression for ts squared, that would be t squared minus tn squared, which would eventually lead to sigma 1 minus sigma 2 squared by 4. You can check this. So eventually this is your direction of this is the magnitude of the maximum shear. Okay, and in which direction is it happening? So that of course is not decidable. Okay, you see there are two principal stresses associated with here. Okay, and the two principal stresses, let's say, have two arbitrary values, and without knowing their values I cannot figure out the direction of traction. Okay, of course the normal component of the traction is let's say this one along the normal. Okay, but the other component, without knowing that, one thing for sure, that would have no component along uh, your n3. Okay, so it would be lying on this plane. I mean the n1 n2 plane, the traction itself along with the normal would lie on the n1 n3 plane, although the normal is perpendicular to a plane that is actually normal to n1 n2 plane. Now this much is the shear component, right? So without knowing, um, so it's the direction would be, you see, normal to n on the n1 n2 plane. Okay, but without knowing the values of sigma 2 and sigma 1, I cannot figure out how much would that be. Okay, so this is your so now the thing is, like with principal stresses, when we are looking for an optima, we got three different stresses: sigma 1, sigma 2, and sigma 3. Okay, it cannot happen that all of them are maxima. Okay, as it turned out, one of them was a minima. Okay, if I assume sigma 1 greater than sigma 2 greater than sigma 3, the algebraic values, then sigma 3 is the minima, sigma 1 is the maxima, and sigma 2 is kind of the saddle. Okay, where you can think of that it's neither maxima nor minima. Okay, something like this. If I were to change the orientation, and this is what I'm getting, let's say, so sigma 1 over here, sigma 3 over here, and or maybe sigma 3 over here, sigma 1 over here, and this is what is sigma 2. So same thing happens with the shear, and this time I'm getting three potential maximum shears. Okay, of course the minima is zero, but there are three possible maximas. We deliberately chose alpha and beta such a way that we should get the maxima. We got rid of the case where the value of TS squared should be zero. So whether TS is positive or negative, the value itself should be maxima. The absolute value should be a maxima. Now, so 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 the maximum shear, the direction of maximum shear or the maximum shear stress, only makes sense once you talk about the same thing, the direction of maximum shear or the shear stress value on a given plane, perpendicular to one of the principal directions. That means on one of the principal planes. So we can talk of maximum shear on one of the principal planes. In this case, it is the plane is N3. Okay, and then on the plane uh, N1, N2, uh, uh, at an angle of 45 degree. You see, if I extend this line, okay, that also makes 45-degree angles on either of the sides. So at an angle of 45-degree, that actually is parallel to the second normal that we showed. Okay, so so on that direction would be acting your shear. Okay, so when we are talking about the maximum shear, okay, there are three possible solutions, okay, to the same maximization problem. Um, and the solution depends on which principal plane are you taking. Okay, and if you take different principal plane, you are going to get different directions of maximum shear stress and different maximum shear stress values. Okay, and if I am looking for the global maxima, I should be comparing the absolute values of these three quantities. Okay, and the one which is the maximum of the maximum is actually used for the design purpose. Okay, is it clear?
Yes, sir, clear.
Okay.
Yes, sir.
Okay, so next we would move on from here to representing stress in components. Now I'm not talking about initial components. like sigma xx or sigma xy. I'm talking about the hydrostatic and the deviatoric part. Okay, and this part uh, I would probably be discussing a little bit about the elasticity as well. And since you have uh, theory of elasticity covered in extensive manner in previous semester, so I'll be rushing through this part. Okay, just for the sake of completion, I'll be going through this part. Okay, so the stress tensor, or very familiar Cauchy stress tensor, can be shown uh, composed of two parts. This part is called the hydrostatic part. Should it be minus pi? Yeah, it would be minus pi. And then a deviatoric part S. This is an um, identity matrix. Okay, so of course each of these matrices are symmetric matrices because the stress tensor is symmetric. So no way deviatoric stress is not symmetric. Okay, so what is this hydrostatic part? So we realize that the trace of the stress tensor is sigma xx plus sigma yy plus sigma zz, which is also sigma 1 plus sigma 2 plus sigma 3. Okay, and let's take an average of that, and that would be trace of sigma by 3. And that actually is your minus p. Okay, so this part has the same trace as sigma. Okay, because minus 3p, because this part is essentially sigma m times I, or 3 sigma m is essentially the trace of this tensor, which is essentially the trace of the stress tensor. And since the trace is a linear operation, the point being trace of a plus b is obviously trace of a plus trace of b. That basically means trace of the deviatoric stress tensor is 0. And the deviatoric stress tensor is simply sigma minus sigma m times I, which basically means the shear components such as this is same as the stress tensor. But let's say if I take a normal component, that is going to be which basically means okay. Why do we talk about this deviatoric part right here? Well, uh, once we enter into plasticity, we would realize that this is the only component of the stress tensor that we are interested when we are talking about plasticity, at least metal plasticity. Of course, there are plasticity formulations where the this part would become very important. Okay, for example, in Drucker-Prager models, Drucker-Prager plasticity, where we are talking about soil plasticity. Okay, now, of course, soil plasticity is something that mechanical engineers not are not as much bothered about. Okay, that would be more suitable to civil engineers. Okay, or when you are talking about uh, little bit of plasticity that the brittle material has. Okay, we probably have to talk about the hydrostatic part as well. Now, when it comes to metal plasticity, this part essentially, I mean, as have been shown by different authors, that we can solely rely on the deviatoric part. Okay, the hydrostatic part has very small role to play. This is because the deviatoric part is associated with mostly shear and uh, and of course, it's not just shear components. There are normal components. Okay, but as you can see that the hydrostatic part of the stress is zero. Now, if we dive in detail, which we would do, we would realize that the deviatoric part of the stress is not associated with any form of change of volume. Of course, when we are talking about change of volume, we are definitely talking about strains and not stresses. So all I'm trying to say here is the deviatoric part is not responsible for any volumetric strain. And as it turns out, the metal plasticity is kind of volume preserving. Okay, it's not, don't take the word literally. It's not that the volume of a metal cannot be changed uh, through plastic deformation. That's not true. But when compared to its other components of the strains, for example, the normal strain, okay, the volumetric strain is much smaller. Let's say if I take a metallic rod and if I elongate it, the axial strain that it has is much more compared to the volumetric strain that the material develops. Okay, uh, so that's where the deviatoric stress has a role to play. And when we enter into plasticity, we would also realize the plastic strain rate itself is proportional to deviatoric stress strain rate, of course. Okay. So we'll look into all of that, but let's start with little bit of elasticity, and let's look at this different stress components in light of elasticity as well. Okay, so this is the simplest representation of elasticity using Lame parameters. These two parameters, lambda and mu, are the Lame parameters. Okay, so this expression is the only way our version of elasticity can work, which is linear, elastic, and isotropic. Now, this expression right there is the necessary and sufficient representation of linear, elastic, and isotropic part. Okay. Now, I would not, I'm not going to prove that this is the necessary condition, but that this is a sufficient condition I can prove that. Or yeah, which means I can show that if sigma is a function sigma hat of epsilon, then sigma hat of q epsilon q transpose is q sigma hat q transpose. First of all, this expression is by definition linear. You see, it involves a linear function trace of epsilon in the first term and simply the scalar multiplication of the of epsilon in the second term. Okay, so this obviously has to be a linear representation. Okay, that's obvious. But how do I know this is elastic? The reason I know this is elastic is that for a given value of strain, and this time by value I mean the entire 9 components of the strain, values of each of the components, for a given value of the strain, there is only one stress component. Because again, this representation is linear, which means it doesn't matter whether you are loading or unloading, whether you had previously loaded to a certain stress value, none of that matters. So history doesn't matter. And you are always, for a given strain value, you are always at the corresponding stress value and all the 9 components of it. Okay, which basically means the loading and unloading curve together do not form a hysteresis loop and do not enclose an area which can represent the energy dissipation. The loading and unloading curves are the same because again this is linear. So so this has to be elastic as well. Look at this expression. This expression says nothing about the loading curve, the unloading curve being different from the loading curve. Now, when it comes to the third proof, the isotropic one, which basically means that the moduli, such as Young's modulus, I mean, in general, they can be defined like this: EYY, EZZ. Okay. Then there are shear moduli. And there are Poisson's ratios. Okay. And there are 6 of them in general. For an orthotropic material, there would be this many parameters. Okay, material parameters. But if we are talking about isotropy, again, imagine we are talking about multi-grain material. Grains are oriented in arbitrary fashion. Okay, and there is no directionality, no direction preference. Hence the isotropy. In a situation like that, each of these quantities should be equal to one single E, and this all of this should be G, and all of this should be nu, and this G would be this quantity in isotropy, which would mean that, let's say, epsilon would be, let's say, epsilon xx, epsilon yy, and gamma xy. Okay, again, this is a void notation or vector representation of the strain, and that too in 2 dimension. And let's say it is 1 0 0. Okay, and then in the second situation it is 0 1 0. Okay, so as we know that epsilon xx is Okay, and let's say and shear component is simply mm, G, right? So, and then there is another component. There would be epsilon ZZ, which would be okay. I'll not go into epsilon ZZ. Just assume that we are working in plane stress condition, which is just for the sake of simplicity. Okay, sigma ZZ is 0. So if you look from here, then sigma XY is 0, and then from this second expression for the first case, sigma YY is nu times sigma XX, and that basically means sigma XX is E by 1 minus nu squared sigma XX. Sorry, epsilon XX. Okay, and in the second situation, sigma XY is still 0. Sigma YY this time is E by 1 minus nu squared epsilon YY, and sigma XX is mu E 1 minus nu squared epsilon XX. Okay, sorry, epsilon YY. Okay. So again, a strain value of 1 doesn't make any sense, but all I'm trying to say here is that as if when the strain rotated, okay, when the strain went from in one direction to another direction, so basically you can think of the strain being kind of rotated from x direction to y direction. The stress also got rotated from x direction to y direction. Okay, so so you can think of the entire strain matrix being rotated, and accordingly the stress matrix also being rotated, and that is the essence of isotropy. Okay, so this expression right here should be able to, if proven true, this expression right here should be able to prove the isotropy of the representation. So that's what we are going to do now. Okay, so so first of all, this expression, the left hand side, should be lambda times trace of q epsilon q transpose. Then the identity matrix can be written as q times q transpose plus twice mu q epsilon q transpose. But we know that trace is an invariant and it doesn't change when the matrix is rotated. So it essentially is a trace of epsilon. And this matrix right here, q times q transpose, can be thought of q times I times q transpose. Eventually, I can write this to be q times lambda trace of epsilon times I plus twice mu epsilon. Again, mu is a scalar, so I can take q out of it. So q transpose, which is basically q sigma hat q transpose. So which means if the strain rotates, the stress also rotates by the same amount. Okay, and that essentially proves the isotropy of the material. Okay, is it clear?
Yes, sir.
Yes, sir.
So stress is lambda times trace of epsilon times I plus twice mu epsilon, right? So it's in linear elasticity. So that can also be rearranged into okay. So as you can see, I have decomposed the strain matrix into two parts. Okay. One kind of is the so so if you look at this part, okay, this part is actually the volumetric part of the strain, okay, or and this part right here is is called the it's kind of like the deviatoric part of the strain. That means this part is not the trace of this part is actually zero, okay. And if you compare with the earlier representation, or if you compare with the earlier representation, the entire left term on both the expressions actually are same, and entire right term are the same, okay. So this part is where, so what we are doing here is, you know we are decomposing stress into a hydrostatic part and a deviatoric part on both the expression. Now one can show that the hydrostatic and the deviatoric part are you see are your orthogonal to one another, okay. So the representation is unique. My point being that mm, the inner product of I and S, okay, is is summation over delta ij, summation over I, summation over j, Sij, okay. And that is essentially only true when it is summation over I, Sii, which is the trace of S, and that is equal to 0. The point being, see, this is the um, inner product of tensors. And if you can think of matrices as vectors, okay, so that is kind of the dot product. And this makes the hydrostatic and the deviatoric part orthogonal to one another. So every time I'm able to decompose stress into one hydrostatic and a deviatoric part, that representation is unique, okay. So all I'm trying to say here is the terms in the bracket are identical. Now what we see here is that S is essentially proportional to the deviatoric part of the string. Proportional. Again, of course, all of this happening in the domains of elasticity. But that being said, this part of the strain and the stress, they are essentially proportional. Okay, just scaled up and scaled down. Whereas the other part, again, they are also proportional, but for the other part, we realize this. And I am sure that you know that this actually represents the volumetric strain. Why volumetric strain? Let's say if you take a brick of some sort, and then um, the volume, new volume after deformation is Lx times 1 plus epsilon xx, Ly times 1 plus epsilon yy, and Lz times 1 plus epsilon zz. Lx, Ly, and Lz being the dimensions of the x, y, and z direction. Then it is Lx, Ly, Lz, the original V0 times these three terms when multiplied gives you epsilon zz plus order epsilon squared. Okay, so basically this becomes the volumetric strain. Okay, so this is how the volumetric strain relates to P. Okay, you see a positive pressure would compress something, right? So with a positive sign on the volumetric strain, it is associated with a minus P, and and the term that comes in between, so that is actually your bulk modulus, which is, so that is, and you already know how bulk modulus looks like. Okay, and to be frank, this M right here is actually your shear modulus. Sorry, it's not an M, it's a mu. So mu is your shear modulus. So the second parameter in the Lame term is actually your, so that's why I was referring to this deviatoric part of the uh, stress being kind of the shear component of the stresses. It's not entirely shear, but the point is uh, it is associated with that part of the strain that has no volumetric deformation. Okay, so basically all I'm trying to say is this part doesn't have a volumetric strain. If the only strain component was this much epsilon d, so then the body would not be having any amount of volumetric change. Okay, again, all of these talking from the domains of small strain. As you can see, I'm ignoring this part right here. So okay, so now please write down these expressions right here. Now if I were to write stress in void notation in the form of a vector, which basically is sigma xx, sigma yy, sigma zz, sigma xy, sigma yz, sigma zx. So I'm just trying to write down the full 3D elasticity matrix for which is D for linear elasticity with isotropy. You see, gamma xy is as we discussed earlier, this is simply sigma xy. This is twice mu epsilon d xy, or twice mu epsilon xy, because the divisory part preserves the shear components. So mu times gamma xy, right? But as we know, sigma xy is g times gamma xy. That eventually gives us mu equals g. So gamma xy, as we know, is twice epsilon xy. So this is how we write it. So mu, mu, and mu, the lower square. Of course, the shear strains do not contribute to the normal stresses, and also the normal strains do not contribute to the shear stresses. Okay. Now we are left with the through normal stress components. So if you look carefully, in this expression, it is lambda times epsilon xx plus epsilon yy plus epsilon zz plus twice mu epsilon xs, which basically means there is lambda everywhere plus twice mu in the diagonal terms. Okay. And this is how you populate the entire elasticity matrix with Lame parameters, and you only need two. That means you either need lambda and mu, or the shear and the bulk modulus, okay, or the Young's modulus and the Poisson's ratio. Okay, so what I need you to do is substitute the expressions for lambda and mu in terms of Young's modulus and Poisson's ratio. So this is your assignment for the day, and with that, I believe mostly we are at the end of what we wanted to discuss about the elasticity of the material. So try to get the expression for lambda and mu with respect to E and nu. So mu you already have. Try to get it for lambda. Okay. So as you can see, lambda is bulk modulus times bulk modulus minus twice mu by 3, and mu is this expression. Substitute over there, and you will have the lambda value. Okay, and then substitute over here. Okay, and try to get the final expression for the elasticity tensor with respect to Young's modulus and Poisson's ratio. Okay, so with that we will stop for the day. Let me know if you have any queries.